Hello, everybody, and welcome to this season 9 of the Law Physics webinar cycle. So today we are going to have a very interesting talk. Don't forget to subscribe to the YouTube channel or also to our Facebook chat. And sorry, because I have a little bit of feedback of myself. Okay, so today we're going to have a very interesting talk. Our speaker is going to be Sergio Palomares-Ruiz. He is from the Instituto de Física Corpuscular in Valencia, and he have done a very large career doing some postdocs, once in Vanderbilt in USA, UCLA, also in UK in the Institute of Particle Physics Phenomenology, also in Portugal, in Lisbon, in the CFTP and IST. And finally, he's in the Instituto de Física Corpuscular, where he's getting a permanent position there. So, Sergio, if you are there, you can start your webinar whenever you want. So, and the topic is neutrino tomography of Earth.
Okay, thank you very much for the nice introduction, Roberto, and for giving me the chance to give the talk. So let me just share my screen. Okay, do you get to see the slide?
Yes. Perfect.
Okay, so let me start. So I'm going to. So again, thank you very much for your introduction and for inviting me to give this talk. So I'm going to present the first tomography of the Earth using neutrinos, and this is a work I've done in collaboration with Andrea Dodini and Jordi Salvador that we recently published in Nature Physics, and. Basically, you know what, probably everyone knows what a tomography is. Basically, this is an imaging technique of a cross-section of a body using some kind of wave. Well, an example of that is when you go to the doctor to get a CT scan, which is basically a series of kind of X-rays, radiographies of your body. And here, the role of the X-rays is played by neutrinos, and in particular, atmospheric neutrinos. The role of our body is played by the Earth, and the photography played where the image is taken is played by a neutrino detector, and in particular, IceCube neutrino telescope. So let us start with what we know about the body of study, which is the Earth. And to do that, I'm going to start with some early hypotheses of what the interior of the Earth may look like. Actually, I'm going back to the 17th century with some early, probably crazy ideas, and I'm just pointing to probably the first hypothesis based on observations about the interior of the Earth, and this is the so-called hollow Earth. This was done by Edmund Halley, which is the famous astronomer that named the famous comet in the late 17th century, and he was trying to understand the variations the variability of the magnetic field of the Earth, and in order to do so, he proposed that the Earth was made of basically 4 concentric shells that were moving independently, and within each cell there was probably an atmosphere, and he didn't even disregard the possibility that there were living beings in each of these shells. And but this is not even the craziest idea that happened in the centuries to follow. Actually, there were even crazier ideas in the 19th century. For instance, there was a modification of this hollow Earth proposal, in which they considered that the poles were not there. Actually, there were holes in the poles, and actually one could access these different internal shells of the Earth through the poles. And there were even crazier ideas. There was this idea in the late 19th century saying that we don't actually live on the convex surface of the Earth, but we actually live in the concave surface. Basically, we live within. So everything is within the Earth. Actually, everything means everything, the whole universe. And all these ideas actually got into the 20th century. And for instance, just this excerpt from this writing on the early 20th century. So let me just read what they said. They said, the Earth is hollow, the poles alongside are but phantoms. There are openings at the northern and southern extremities. In the interior are vast continents, oceans, mountains, and rivers. Vegetable and animal life are evident in this new world, and it is probably peopled by races yet unknown to the dwellers upon the Earth's exterior. So let me for the rest of the talk see if we have all these beasts and creatures inside of the Earth. So what is the modern view of the Earth interior? So basically, the Earth is made of several layers. Basically, there are two big structures. One is the core of the Earth, and the other is the mantle. The core is basically made of iron and nickel, and the mantle is made of rock. There are, within the core, for instance, we have two major layers. One is the inner core, which is basically solid, and the other one is the outer core, which is liquid. And this is very important, the fact that the inner core is solid and the outer core is liquid, because the movement of the outer core is what basically generates the geodynamo of the Earth and generates the magnetic field of the Earth, which is fundamental, for instance, for making up the atmosphere of our Earth. So this understanding the core is a critical issue to understand the magnetism of the Earth. Then we have the mantle. We have the lower mantle, which is basically rock solid, and we have the upper mantle with different compositions. Basically, it's basically rock, but it's solid, plastic, and solid. And then we have the crust, which is just basically the few tenths of kilometers below our feet. And how do we know about all this in modern days? So basically, what we do is to use seismic waves, or geophysicists use seismic waves. Basically, there are of the order of 100 earthquakes per year with magnitude larger than 6, and thousands of them with smaller magnitudes. And basically, there are two types of waves. On one side, we have P waves, which are longitudinal, which are compressional, and they travel through solids and liquids. And on the other hand, we have S waves, which are shear waves, and they are transversal, and they only travel through solids. And this is important because actually the fact that the S waves do not travel through the outer core is what brought geophysicists to infer that the outer core is liquid. And as I said, this is very important. But all this inversion problem from the measurements of the waves to the understanding of the Earth's interior is a rather non-trivial problem, because the propagation, the velocity of these waves and the propagation itself depends on the composition of the medium, not only if it is solid or liquid, but also on the composition, on the temperature, on the pressure. For instance, we have all these properties, for instance, about the core are inferred only indirectly and poorly. So, but we can also have other information, for instance, from gravitational measurements. We can measure the gravity field with satellite laser ranging, which is similar to GPS, just more precise. And in that way, we can measure the product of Gm, where G is the Newton's constant, with great precision. But in order to get the mass of the Earth, we need to know what the value of the Newton's constant is. And actually, this is done in modern days, just basically with modern variations of the Cavendish experiment. And here, the Newton's constant is determined in 1 part in 100,000. So actually, the determination of the mass is as a combination of these two measurements, and the uncertainty in the mass is driven basically by the uncertainty in the gravitational constant, which is basically 1 part in 10 to the 5. So the mass of the Earth is of the order of 6 times 10 to the 24 kilograms. But we can also determine, for instance, the moment of inertia of the Earth by just doing gravity models of the Earth, and basically just perturbing these models, and basically the coefficients up to, I think it's degree 2, are related to the elements of the tensor of inertia, and there are many gravity data that can be used to infer those coefficients, and from them to get the moment of inertia. So the average moment of inertia of the Earth is written this way. So it's basically at the level of 10 to the -4 in uncertainty. So with all this at hand, geophysicists could obtain these models of the Earth. One can do a simplified model of the Earth, assuming that the Earth is spherically symmetric. This is just a first-order approximation, which works reasonably well. And as I said, from seismic wave data, and imposing, and this is important, the Earth's radius, the mass, and the moment of inertia, as I just mentioned, measured by gravitational data as additional constraints, the geophysicists can obtain these density profiles. And the one I'm showing here is this famous preliminary reference Earth model that, if you work on neutrino physics, probably you have used sometime in some of your papers. Basically, the overall picture is that we know the density distribution of the Earth within a few percent over depths of several hundred of kilometers, average over hundreds of kilometers. There are some properties or some features that we don't understand at that level. For instance, we don't you see here the transition between the inner core and the outer core, and the difference in density has an error of 20 or even more, 30%. But on average, we know the density is within a few percent. But understanding, for instance, the core, as I said before, is fundamental to understand the Earth magnetism. And all geophysicist methods do it in an indirect way, and in many occasions, as I said, the propagation of seismic waves depend on the properties, temperature, density, and these things are not very well understood and have to be extrapolated from models from geophysics. So it would be good to see if we can actually learn anything from about these from in some other way. So the question is there any other way to study the Earth's internal structure beyond seismic waves and gravitational measurements? And as you can obviously guess, the answer is yes. We can use weak interactions. We can use neutrinos. And for the rest of the talk, I'm only going to use weak interactions and only weak interactions to make these measurements. This is not a new idea. This is an old idea, actually from the 70s. It was first mentioned in a CERN report in 1973 that got never published, as far as I know. And then it was also mentioned in a talk in 1974. And in these two early proposals, they were considering man-made neutrino beams, basically beams with energies of TeV, just traveling basically big sections of the Earth. Basically, those beams were not visible then, are not visible today, but that was the idea to do this. And since then, basically, there have been different ideas to use neutrinos to understand the Earth's interior. And let me just quickly go through them. So this is the so-called oscillation neutrino tomography, in which case what one uses is the coherent effect of matter effect of neutrino propagation. This is the same matter effect that one uses, for instance, in lumped line neutrino experience, for instance, to determine the mass hierarchy, and any other basically propagation of neutrinos affecting this coherent matter effect. This is basically related to the real part of the forward amplitude of neutrino-electron interactions. And there are different type of neutrinos that one can use. One can use man-made beams, solar neutrinos, supernova neutrinos, atmospheric neutrinos. Here I'm just quoting the first papers in which these kind of things were discussed. And this is important or can be interesting for energies where matter effects, usual coherent matter effects in neutrino propagation take place. So this is basically for energies below 100 GeV, and that depends also on the type of source. If we have atmospheric neutrinos, solar neutrinos, whatever. Then we have also absorption tomography, which is important for energies, say, above TeV or so. And this is actually the original proposal was is of this type. This proposal in 1973 and 74. Then there were other proposals, for instance, for using cosmic neutrinos that could have also very high energies, and also atmospheric neutrinos. Basically about a decade ago. This is using the incoherent effect in neutrino propagation. So basically this is related to the imaginary part of the forward amplitude, which is related to the cross section. Basically this is the absorptive part. And basically, as I said, there are different ways to do this. And the rest of the talk, I'm going to concentrate on atmospheric neutrinos and absorption neutrino tomography. And then there is a third type of tomography, which is using the diffraction of neutrinos, and this was proposed. It was considered a few years ago, but this is completely unfeasible. Okay, so what are atmospheric neutrinos? I'm going to talk about atmospheric neutrino absorption tomography. So atmospheric neutrinos are those neutrinos produced after cosmic rays interaction with the elements of the atmosphere. So there is a cosmic ray flux that gets into the atmosphere, collides with the elements of the atmosphere, oxygen and nitrogen, etc., and produces pions and kaons that later decay and produce neutrinos basically of electron and muon flavor. And this is a very steeply steeply falling flux of something like e to the minus 3.7, and it is the dominant flux up to energies of about 100 TeV, where cosmic neutrinos start dominating. So why are atmospheric neutrinos interesting for what I'm going to discuss? So first is we have a huge range of energies with atmospheric neutrinos and baselines. So basically we can cover all directions, so we can consider neutrinos crossing the Earth in all directions, and we can study the matter effects, as I said, in all directions with a huge range of energies. For instance, if we consider GeV energies, we can study coherent propagation, basically the usual matter effects in neutrino oscillations. And it turns out that the oscillation for the delta m square atmospheric for GeV energies, the oscillation frequency in vacuum is of the same order of the matter potential in the core. It's also of the same order of the inverse of the size of the Earth, and that implies that we can study, for instance, resonant effects in neutrino propagation at these energies. Then when we go to higher energies, it turns out that the mean free path of a neutrino crossing the entire Earth, the mean free path of a neutrino with energies of a few tens of TeV is of the order of the radius of the Earth. So that means that for neutrinos above, say, a few TeV, the Earth is not transparent anymore, so neutrinos get absorbed in the Earth. So by studying neutrinos of different energies in this energy range, coming from different directions, crossing the Earth from different directions, we can study the amount of absorption of that flux, and from that we can study the amount of matter that this particular flux of neutrinos is experiencing in different directions for different energies. And this is actually the main topic of this talk. So, but before getting to what we did, let me just comment on the very few papers that have been done on this atmospheric neutrino absorption tomography along the years, and there are not so many. The first time that this was discussed, it was about a decade ago by Concha González García and collaborators, and they did a first forecast of, as I said, absorption neutrino tomography using atmospheric neutrinos for IceCube. They considered 10 years of IceCube, and they, for instance, studied how well we will be able to tell that the Earth is non-homogeneous after 10 years of IceCube data, and they concluded, depending on what the control that we would have on the systematic uncertainties, that we could do this between 3.4 and 4.6 sigma after 10 years of IceCube. Then there were a couple of works on forecast for kilometer cube net, with similar conclusions, if I remember correctly. Then there was a work that studied lateral heterogeneities, basically studying the 3D features with IceCube. And for this one would need at least an order of magnitude higher statistics than just IceCube in 10 years. And then there was also another study of the Earth non-homogeneity. And even there was a first attempt using 1 year IFC 40 data, which was too preliminary to actually tell much about the Earth's interior. And so let me move to what we did. So what we consider is the IceCube neutrino telescope. This is a 1 kilometer cube detector, which is placed in the South Pole, basically 1.5 kilometers below the surface of the Antarctica. It consists of 86 strings, which are separated by 125 meters in a triangular grid. In total, it has more than 5,000 digital optical modules, and they are separated within each string vertically by 17 meters. It also has a more densely populated region of digital optical modules, which is deep core. And as I said, this is placed at the South Pole. It was completed in 2010. And neutrinos are detected by the terrain of light emitted by the secondary particles, which are produced after neutrino interactions, either in the detector or outside the detector. Actually, there are different types of neutrino events that IceCube can record. And for instance, in the work I'm going to present, we used 1 year of outgoing high-energy muon neutrino events, which is IC86, so basically the first year of data with the full detector. This type of data uses muon neutrinos, basically crossing the entire Earth. And these neutrinos go through the Earth, and just before getting into the detector, they interact with the surrounding medium of the detector and produce a muon. This muon, very high energy muon, travels and crosses the neutrino and the the detector, and this is what IceCube measures. This neutrino cross, this muon crossing the detector, which has been produced outside the detector. This sample was used and prepared for the IceCube sterile neutrino analysis, so it's exactly the same sample of through-going muons used for that analysis. And in short, it has an energy range, covers an energy range between 400 GeV and about 20 TeV. It covers basically half of the sky, so basically all directions below the horizon. And it has a number of events of more than 20,000 events over basically 1 year, with a huge, very high purity of muon neutrino events. And the most important thing is that all this data set is publicly available and everyone can use. And on the right plot here, I'm just showing you the number of events as a function of the cosine of the descending angle. And on the top histogram is just the full sample. And then we select here higher and higher energy samples with higher and higher energy. And as you can see, this part here, where on the left is for neutrinos crossing the core. As you see, when we go to higher and higher energies, the absorption for neutrinos crossing the core is relatively higher. So this is the way one can test the amount of matter that these neutrinos are crossing as a function of the direction and as a function of the energy. And this is the way we are trying to tell features about the Earth's interior. But in order to do that, let me just tell you what are the ingredients that we need to do it. So first, we need to know what is the neutrino flux, and in order to do that, we need to consider different primary cosmic ray spectra. Commonly, there are popular 3 population models that are used to fit the cosmic ray data. Also, we need to know what is the hadronic interaction model, how these cosmic ray interactions produce showers in the atmosphere, and then which are then the ones that give rise to the neutrino flux. So putting all these things together, one can get the neutrino flux, which is also measured by neutrino telescopes like IceCube and other neutrino experiments. And actually, that measurement of the neutrino flux also can also help to reduce uncertainties on the primary cosmic ray spectrum and on the hadronic interaction models, apart from other measurements, for instance, from cosmic ray data, from LHC data, that are helpful to do that. Okay, so once we have the neutrino flux, and I'll come to the modeling of these and how this affects our measurements later on. Once we have that, we need to propagate neutrinos through the Earth to know how much of this flux is absorbed and how this is sensitive to the structure of the Earth. And we do that by using NEUTRINOS, which is a code, public code, which was created by Carlos Argüelles, Jordi Salvador, and Chris Weaver. And we also incorporate, for instance, neutrino oscillations, although at the energies that we are interested in, this is not really important. And also in the propagation of neutrinos through the Earth, and also in the detection level, we have to care about neutrino interaction with nucleons. At this point, for the energies that we are interested in, the uncertainties in the neutrino-nucleon cross-sections at the level of a few percent. For the antineutrinos is slightly larger, but this is, in any case, as you will see, smaller than the statistical uncertainties that we have currently. And finally, we need an Earth model, which is where we want to fit and to extract from the data. And we tried and checked different modeling of the Earth interior, and we tried using different number of spherical cells. We consider a spherically symmetric model. As I said, we checked with more layers, with fewer layers. We checked that using different density profiles within layers. But in the end, a good compromise was to consider 5 spherical layers with a flat density within each layer, and that is perfectly fine. Any other possibility would give similar results with the current statistics. Basically, what we did was to consider 1 layer for the inner core, 2 layers for the outer core, and 2 layers for the mantle. And finally, we need to know how to map the observed quantities into the relevant quantities like neutrino energy and neutrino direction. And for that, we need the detector simulation, which again is publicly available. Without that, we wouldn't be able to do this type of analysis. So we are using the official IceCube Monte Carlo, as I said, is publicly available in that website. which maps the observables to the interesting quantities as neutrino and direction, neutrino energy and direction. And for this type of sample, the direction of the neutrino is very well known, with an uncertainty below the degree, basically, with uncertainties about 0.5, 0.7 degrees, which is perfectly good for what we can do. And for the energy, things are a bit worse, because recall how these events are produced. This is a neutrino crossing the Earth and hitting a nucleus outside the detector. And so the hadronic shower, which is produced in that neutrino interaction, is not detected. And then we don't know also where the interaction takes place. And therefore, we don't know how much energy the muon loses before getting into the detector. So these two facts give rise to a relatively large uncertainty in the determination of the neutrino energy that produces a particular muon event. But all that is coded in the IceCube Monte Carlo that we use. Okay, so once we have all these ingredients, we do a binned maximum likelihood analysis, and our idea is to determine the densities of these 5 layers of the Earth, as we have for model the Earth. We also include a number of nuisance parameters, like detector efficiency, like the efficiency of the digital optical modules, and some other continuous parameters related to the atmospheric neutrino flux, like the normalization, the pion-to-K ratio, the spectral index, etc. Then there are other systematics, as I also mentioned, like the primary cosmic ray spectra, the hadronic interaction models, neutrino cross-section. I'll comment on those later on. And in order to infer the parameters with the data using this maximum likelihood analysis, we use multi-nest. And just one comment, which is important, is that in this work, we don't take into account the uncertainties due to the optical properties of the ice, just because in the way this is available with the IceCube Monte Carlo was not precise enough for our analysis. But this is potentially something that could have an impact on the results. Okay, so the first thing is to ask if the Earth is actually there, if we have Earth below our feet. And by that, for instance, we plot here the ratio of the data to the expectations with no attenuation. On the left plot, I show you this ratio as a function of the cosine of the zenith angle. So on the left is neutrinos crossing the core, and then to the right going to lower and lower depths. And as you can see for the plot on the left, the absorption only takes place, is very little absorption and only takes place for neutrinos crossing the core, but this is because we are using all events. Recall that the atmospheric neutrino flux is a very steeply falling flux, so basically all the statistics is dominated by low energy events, for which absorption is almost negligible. But this is using the full sample is very important to fix the normalization of the atmospheric neutrino flux. Then on the right, we select events with energies about 5 TeV. And in that case, I note the difference in the scale on the y-axis. The absorption is significantly larger, as you can see here. For instance, for core-crossing neutrinos in this energy range, attenuation can be as much as 50%. And well, that is what we use in order to infer the amount of density, the amount of matter that neutrinos traverse in different directions. Okay, so with all this, basically this is the main result that we got, which is the one-dimensional density profile. This is the first time an Earth tomography has been performed using actual data with the neutrinos. And this is the density as a function of the radial distance from the center of the Earth. In red, you see this is the Prem profile, and in blue, the dots and the histogram represent I think this is the 2 sigma 95% confidence level measurement of the different density of the 5 layers of the Earth. So you see that our measurement with the neutrino data is not our determination of the density profile is not that precise, but it agrees completely with the geophysicist measurement. But it's important to note something. In this Prem profile, the Earth mass and the moment of inertia are external constraints which are imposed, and that significantly reduces, for instance, the density of the uncertainties on the density of the mantle. We are not doing that. So as I say, up here, unlike reconstruction with seismic data, no constraint on Earth mass or moment of inertia is taken into account in our measurement. So this is the measurement using only weak interactions. And with that, we can, once we have this, we can see what other quantities related to the Earth interior. For instance, we can weigh the Earth's mass. And this is measuring the Earth's mass with the weak force. So here there is no gravity involved. This is just using the weak force, and this is our result. So our result is fully compatible with the gravitational measurement. Of course, it's very far from the precision that one gets with gravitational measurements. But we are able to see the Earth at more than 4 sigma with neutrinos. And this is the measurement. As I said, this is the first time the mass of the Earth is weighted with a weak force. Then we can also, for instance, measure the core mass, which is fully consistent with what one gets from the Prem profile. One can also, for instance, measure the moment of inertia using, again, only the weak force. And again, this is the result that we get, 6.9 times 10 to the 37 kilograms meter square. And this is fully compatible with 1 sigma to the gravitational measurement. Of course, the error is bigger. Actually, we can even do a first estimate. This is the moment of inertia, which is measured divided by the moment of inertia if the Earth was homogeneous. And we see already here that this is way at 1 sigma, but one can do much better on this test of homogeneity of the Earth. And actually, one can ask what is the core mantle discontinuity, again, using only the weak force. And this is the result we get. And a denser mantle has a p-value of just 1%, which is already very good. What else? So I told you that all these measurements that I mentioned include all these nuisance parameters that I mentioned before, but also we studied the impact of discrete systematics, like for instance the study of different atmospheric neutrino fluxes. And in these panels, I'm showing you the Earth mass, I'm showing you the mass of the core, the moment of inertia, and this difference of the average density in the core and in the mantle. And different colors here represent different hadronic interaction models. And as you can see, the systematics that we have from using different both primary cosmic rays spectra and different hadronic interaction models are at the level of 20–30%, which are slightly smaller than statistical uncertainties, but already important. And these systematics are mainly driven by our knowledge of the hadronic interaction model. So this is something that would potentially be critical with more data when statistical errors decrease, and this could be one of the dominant sources of systematic errors in this type of analysis. But we also ask about the future, actually the present, and I will explain why I say the present. We did a forecast, actually very rough forecast for 10 years based on the 1-year data. And basically what we concluded is that one could get the mantle density within a few percent error. So this is already at the level of geophysicists' determinations. We can, of course, do a finer modeling of the Earth. Actually, in this forecast, we just wanted to compare to what we have with 1 year. So basically, we did the same 5-layer modeling of the Earth, but we also checked that this will necessarily need to be improved with more data, with more layers. And also, we might be able to test discontinuities, for instance, the core mantle boundary, the position of the core mantle boundary. We might be able to test, and maybe in the future, I don't know if with 10 years, probably not with 10 years, maybe we can already try to see if we can detect the discontinuity within the core, between the inner and the outer core. And as I mentioned in the previous slide, knowledge of the hadronic interaction model might become a crucial source of systematics, and we might want to reduce that in order to reduce systematics in the future. And with all this, basically, I just show you the forecast for 10 years. The blue is what I show you with the actual data, and the red is the histogram with the 5 years, with the 10-year forecast. and the improvements that we can get. As you see here, the mantle density can be determined with a few percent. And as I mentioned, this is the future, but actually is the present, because there are already 7 years of data which have been already recorded by IceCube. So we used 1 year data, but this was between 2011 and 2012. So we have all these 7 years of total data that have been collected, and it's a matter of doing the analysis and see what we get. So practically the red is probably what we have now and not the blue. Okay, so let me just conclude. So after 44 years of being proposed this idea of neutrino tomography, we have performed the first Earth absorption tomography with neutrinos. This is the first measurement of the Earth's mass and moment of inertia using uniquely the weak force. And well, you have seen this is not precise, but it might become a technique which is complementary to other geophysics studies like seismic wave studies. We did an analysis with 1 year of data, but there are already 7 years of data collected by IceCube. And in the future, we will have other experiments like kilometer cube net, Baikal GBD that could add to this kind of measurements. So thank you.
Thank you very much, Sergio. So, okay, let me just, sorry. Okay, so we are here. So, okay, thank you very much, Sergio. So we could start with the session, with the question round. I don't know if there is people here in the audience of the Hangout that you want to ask questions to Sergio.
I have a question.
Okay, please.
So first of all, thank you very much, Sergio, for this super nice talk. So I was curious, you said at some point that one of the ingredients of your feed is the model of the Earth. So you have these 5 layers for the Earth, right? Hello? Can you guys hear me?
I can see you. I can see Sergio.
Sorry?
Okay, now he's back.
Were you hearing me, Sergio?
No, I don't see, I couldn't hear anyone.
Can you, Sergio, hear us?
You want me to close the... So let me see if I can...
I will
I'm just trying to... Can you hear me?
Yes.
Yes, I can hear you. But
okay.
Maybe you cannot hear Nicolas.
I cannot hear anyone, only you.
Only me. So I'm the lucky one. So, okay, maybe in the meanwhile that Nicolas...
I will write the question to you.
Yes.
I see Nicolas moving the mouth, but I don't hear.
Yeah, we have the same problem in the last webinar. Nicolas got mute. So anyway, let me ask you a question because I have many. So one question that for me was puzzling, but you kind of tried to answer there were previous studies about that, but is it possible to done with the future neutrino telescope, like for instance KM3net, because you present a forecast, but is it possible that KM3net can match the sensitivity and the resolution that has IceCube for this kind of studies?
Oh yeah. They will be able to that. Bear in mind that the energies here is few TeV what matters. So KM3net has comparable and in some cases better resolution for some type of events than IceCube. So for instance, for cascades, one could even consider using cascades, because in the case of IceCube, cascades have uncertainties of the order of 10 degrees or so. So that makes using cascades more difficult. For KM3net can get to uncertainties of a few degrees for that. So one could also use cascades, which for this analysis is only done with muons. So yeah, definitely they will add. And we are in conversation with people.
Yeah, in fact, maybe now I don't know if Nicolas can unmute just to test if he can ask the question. Otherwise, I can ask.
Yes, Sergio, can you hear me?
Well, what do you mean by without prejudices? We don't have any prejudice.
Yeah, that is the question that Nicolas has.
We need to model. We need to reconstruct something, right? So we need to fit something. So we need to do a modeling. What we did is we checked the different modelings. So we checked using more layers. We checked using different densities within layers, and we checked different modeling of the Earth. But we need to fit some model to the data. And what we did is, after checking different models, we concluded that no matter what the model is, as long as at least we have 5 layers, because the statistics allows us to do 5 layers. But if we go to 7 layers, we go to 10 layers, we go to 20 layers, we can do as finer modeling as we want. But given the statistics, we want to learn anything else than what we are getting with 5 layers. So 5 layers is not like that. Doesn't mean that we are constraining our potential knowledge of the Earth from here. It's just the limiting fact from the statistics that we have. This is what I was saying, that when we go to the forecast with 10 years, we did just the same type of forecast with 5 layers, but actually with 10 years, one can do better, and we checked that one can do better. And Nicolas is telling me to read the question, so maybe I read the question after my answer. So he said that I think that for the fit you used a model for the Earth with 5 layers, it's not clear to me why such a model is needed. Can you just redo the analysis without a model for the Earth, without prejudices, and rediscover the Earth inner structure? And I think that was it. And my answer was, we have no prejudices on this.
Very good. So I don't know.
I have a question.
Yeah, Joel.
Do you hear me?
I can hear you.
Does Sergio hear me? Apparently not. Oh, this is interesting. So maybe I'll type it, or
okay.
I don't hear.
This is see again once more. I just reset the no. Okay, so I'll type
just to Sergio.
Yes, you can type the question to Sergio. I'm gonna ask another question that I have here. So,
but if you write it, I will read it and then I will answer. And I will remember to read it before answering.
Yeah, for the audience, they can. Okay. Also, okay. First, let's go to some questions from the audience in YouTube. There is a guy that his name is L4Key3D41MON. Okay.
This is maybe a model of the Earth.
Yeah, he's asking, could you do a similar experiment with different detectors? Could this be performed with a dark matter direct detection experiment or a CNUSN experiment? That could be the limitation in these cases.
What is the last one?
CNUNS. I don't know
you mean the coherent type of experiment?
Coherent experiment, yeah.
Well, the key here is statistics. So we need a huge detector. So I don't see. I mean, we not even with the current data of Antares. This is not good enough. Antares is about 10 times smaller than IceCube, and is not good enough to do this. And we are trying to see if we can get anything out of Antares data, but it's not. So it's just the key is statistics. So the answer is no. We need a huge detector.
Yeah. So
this is a statistic. We are interested in neutrinos with energies, say, around and above TeV. So the amount of events that you get with a detector of that size is basically 0 or very few.
Yeah. So sorry.
Okay, my question is done. It's
okay. Joel Jones is asking.
Yeah. So I read that. So at the beginning of your talk, you mentioned that you were focusing on neutrino absorption. However, when using NEUTRINOS, you did add the matter effect in oscillation. So my question is, what is the role of matter effects in oscillation within your results? None. There is no effect, basically. I just meant we just added it for completion. But the lowest energies, and these are muon energies that the sample has, is about 400 GeV. At those energies, the effect of oscillation is really minimal. So it has I mean, I don't remember exactly, maybe at the level of few % effect at those energies. but it has no impact on our results. It was just for completion.
Okay, so there is a continuation question from this L4K. They said if you change, for instance, the exposure of your experiment to increase more the time of integration time for your result. In the case of dark matter experiment, thinking about neutrino backgrounds or so on. So I guess it's, I mean, for the lifetime
No,
of
but I mean, always no matter what you do. I mean, with dark matter detectors, you cannot do anything because it's just the size. So, what type of dark matter detector? You're talking about what, ton detector, kiloton detector? IceCube is a gigaton. And with a gigaton, we have about 20,000 events per year. So, and with 20,000 events per year, we get errors at the level of 15, 20%, or 30% actually. So you go 6 orders of magnitude below, we are talking about 20,000 times 10 to the minus 6. So it's a statistics. We need a statistics, and this the flux of atmospheric neutrinos goes as e to the minus 3.7, and basically we need to go to neutrino telescopes. There is no other way out. I don't see to do a neutrino absorption tomography. A different thing would be to do oscillation tomography. For that, we can do that with GeV neutrinos. We can even do that with solar neutrinos, and for that we can use, let's say, usual neutrino detectors like Super K, or even smaller detectors. But for absorption tomography, the key is size. So for absorption tomography, there is no way, I think, to do it. For oscillation tomography, in principle, one can do, but there is actually, right now, there is no analysis of studying the Earth using oscillation tomography. There are forecasts, there are many forecasts in the literature that have done that, but so far we have no analysis on that. For instance, one could do it, now that we know the value of θ13, one could do that with atmospheric neutrinos. And that could be something to do in the future, and this is something we are thinking also to see if we could do or incorporate that kind of thing. But so far there is no analysis with actual data with oscillation tomography, and for absorption tomography we need neutrino telescopes.
So there is, okay, Joel is still insisting about the question.
Okay. So I'd like to insist with the matter effects. Sorry, no worries. You did mention a paper that considered doing the tomography in that case. Could you comment on that paper? Okay, okay, I already did. Yeah, there, as I said, there are for absorption tomography. Actually, there is larger. I mean, there's a larger literature, and not only with atmospheric neutrinos. There are supernova neutrinos. There are man-made neutrinos like accelerators. There are works trying to see if we can use neutrinos, for instance, to detect oil bags in the Earth, and to see if we can detect, for instance, gas. And there are many works on doing oscillation tomography, as I said, with different type of beams of neutrinos. So far, there is no data. So far, there is no analysis with data.
Okay, there is, thank you. There is a question from the YouTube chat. He's asking, I mean, Arhinjajit Data, sorry if I pronounce it wrong. He's asking, Earth is not a perfect sphere. How do you incorporate this issue? If you
we don't.
Recommend about that, please.
Yeah, so we consider a simple case, which is just a spherical symmetric Earth. Of course, the Earth is not spherical symmetric, and there are inhomogeneities. However, there is actually we didn't do that test, but with the statistics we have, it is not possible. There was this work I mentioned, I think, during the talk. There was a forecast that tried to see how for instance, IceCube could be sensitive to different 3D features in the Earth. And for that, we will need at least 1 order of magnitude higher statistics. So we will need of the order of 100 years of IceCube. or more, probably more. So this is something that in the future, maybe with the generation 2 IceCube, which is 10 times larger, with 10 years of IceCube, maybe adding what we can do with kilometer cube net, and if in the future we are able to do an even bigger version of kilometer cube net, maybe we end up with something like 100-year of IceCube-like data, and with that one can start thinking of 3D features. So far, the modeling we did, the simplified modeling, is more than enough. I mean, it's bear in mind that we are taking 5 layers even within this simplified model. So one could first ask, can you actually do more layers and get finer structure in the Earth within this simplified 1D model? And the answer is no. So getting 3D features is even more unlikely. It's impossible, basically, with this amount of statistics.
Okay, so Sergio, I have a more question. I don't know if other people from here from the Hangout session ask a question, but anyway, so one question I was wondering, does IceCube have is in a better position, like the location, because it's in the South Pole? You are kind of, maybe you are not sensitive maybe to some asymmetries produced by the Earth's rotation or something like that? Or
no, not really.
At this moment, IceCube, I mean, this analysis is not sensitive to a small fluctuation inside the Earth crust. But
no. In principle, no. Actually, as I said, we are doing a spherical symmetric model, so we are not sensitive to those finer structures, and we are doing. I mean, the size of, the depth of these layers is of the order of thousand kilometers, thousands, 1,000, 2,000, depending on the layer. They are not equal. But so it doesn't matter. It doesn't matter with the current modeling. I mean, if we had a detector 100 times IceCube, then probably it would be different, because there can be features that are in one place of the Earth or in the other, and maybe in that case, yes. But with the current statistics, with the current type of detectors that we have, I don't think we are sensitive to these finer structures, 3D structures, and it doesn't really matter. But we will see that. I mean, when KM3net comes into play, we can start trying to see if at some level, just at the level maybe of hints, we can get some 3D differences between IceCube and KM3net data. But this we will know with the data. But it's very unlikely, I must say. We haven't done the analysis yet. This is something we are thinking of, to see if we can get something out of this. But with the estimates we've done, I don't think that with the statistics we have, we will be able to do anything very sensitive in that respect. So no, in principle, it doesn't really matter.
At this moment. So there is, Joel is still asking more questions. It's very...
So final, far-fetched question. Will it be ever possible to constrain neutrino non-standard interactions or light neutrino decay by requiring your result to match with PREM? Yes, but yes, in principle, yes, and actually we have a paper on using actually the same data we used for this analysis to constrain non-standard interaction. This is a paper I did with Jordi Salvador and Nuria Rios and Olga Mena. We used actually the same data set, and we got the best constraints on non-standard interactions on the mu tau parameter. So the answer is yes. One can use this to constrain a neutrino non-standard interaction by imposing that the density profile must be PREM. And they are the best actually in that sector.
Okay, Sergio, we have one more question from YouTube. Mr. Data, he's asking, would you please tell again why you are not using solar neutrinos? He has this doubt.
Why we are not using
solar neutrinos?
Well, solar neutrinos are not do not have absorption in the Earth. Solar neutrinos are in the MeV range. So at MeV energies, the Earth is completely transparent. So one could use solar neutrinos to do oscillation tomography to study matter effects, coherent matter effects on solar neutrinos, like for instance the day-night effect, that is a matter effect, and but not for absorption tomography. So one can use solar neutrinos, but not for this type of analysis. And actually, in the future, the ideally would be to use solar neutrinos, would be to use accelerator neutrinos, to use atmospheric neutrinos at GeV energies, and to incorporate all this data with all the oscillation parameters, neutrino oscillation parameters, and with all that knowledge, trying to see how sensitive we are to these matter effects with, as I said, solar, atmospheric, accelerator neutrinos, and with oscillation tomography, and add also what we learned from higher energies, from absorption tomography, using, for instance, atmospheric neutrinos. But solar neutrinos do not, you cannot do absorption tomography in the Earth with solar neutrinos. The Earth is transparent.
Okay, so let's see if there are no more questions in YouTube. I just have a very small question, because during your talk, you said that you test how large or if your measurement is compatible with the measurement of the total mass of Earth.
Yeah.
What about this if you really incorporate this, like your priors, like all this information from gravity measurement of Earth crust, maybe also the information that was measured, I guess, by Borexino, I guess was the one that the radioactive element inside the Earth crust, just to have a map. Can you get this kind of extra using all the available neutrino observables at different energy scales? I guess that was the neutrino radioactive element that was measured by Borexino, just to see how much radioactive power has the Earth.
Do you mean to use radioactive measure? I mean, neutrinos, or do you mean to use measurements of the Earth mass by gravitational data?
Yeah, just to improve your sensitivity, because now you measure the Earth, the total mass of Earth is compatible with neutrinos and with the gravity observables.
Yeah.
But now, if you include the gravity observables in your analysis, you can make a stronger constraint on the neutrino physics, let's say.
Okay. Do you want me to share window, because I have a slide for that?
Okay, that would be great.
So let me share that, and I'll show you. Is it already sharing? Can you see it?
Yeah, I can see it.
I have some backup slides here. Oh, this is here. This is adding gravity constraints. Basically, the density of the mantle gets determined within a few %, but this is basically geometry. So this is why, for instance, the seismic wave determination, when you add the external constraint, this is what I meant before, that adding the mass of the mantle is about 70% of the mass of the Earth. So once you add that with the uncertainty of 1 in 10 to the 5, then basically you constrain very, very much the density of the mantle, and then you can get it at the level of 4%. On the contrary, the density of the core doesn't change much. So adding this mass of the Earth and a moment of inertia of the Earth as an external constraint, which is basically fixing those given the uncertainties, doesn't change the determination of the mass of the core using neutrinos. So it doesn't change how much neutrinos are sensitive to the core, but it does affect the mantle. Yeah. So this is the answer. So.
Okay, so I don't know if there are any other questions from the people. If not, I guess we are in a good time to, first of all, to thank again Sergio. It was super interesting, the talk. It was very impressive to know how neutrinos can be helpful to understand how what is happening inside Earth, to determine some of the parameters of our planet. So sorry for the noise, there is some construction here in the building. So anyway, so Sergio, thank you for your talk.
Thanks to you for inviting me.
Yes. For all the people that are following us in YouTube, please consider to subscribe to our channel. We're gonna continue with this scheme with this type of webinar that we are gonna continue during the time. So for all the rest of the people that follow us now in the live streaming, thank you, and see you next time for the next law physics webinar.